Welcome back. Today we're going to be looking at chapter 13, which talks about another type of test called chi-squared testing. This isn't x squared, it's that Greek letter chi that some people like to pronounce chi, but it's chi, and it's chi-squared. No, that's the U, that's the A. So, we're going to be looking at chi-squared testing. There's a few different tests that happen with chi-squared testing. And what this is for is it's for when we have multiple proportions or multiple things that we're looking at. So far, what we've done, we've had one thing, like one sample, uh, data and testing, and we've had two sample things where we've been comparing two different samples, but this will allow us to compare multiple things, because a lot of times, like if you're testing a new drug, it's not the drug or the placebo, it's going to be, there's going to be multiple things there. So we're going to test a few different things. The first section is on tests for goodness of fit. Now, this is testing to see if what we think the expected counts or the expected proportions are actually what they are. What I would do first, before anything else, is I would pause me right now. I would go to the store, get yourself a bag of M&Ms, and do the M&M experiment that's on pages 726 or 727. It's also, I'm posting it along with this, but it is a really, really good experiment that takes you through this process step by step. I strongly, strongly recommend doing it. We would be doing it if we were in class. It's always fun because, well, I go out and buy the M&Ms for you, which I can't do at the moment, sorry. But then in class, I get to throw packages of M&Ms at you, and I've never had anyone complain that I threw a package of M&Ms at them. And so, some of you may have actually done this in biology as well. I hear that the biology class has been stealing my activity, and so you may have done that. So, anyway, what you end up doing is you end up doing a test for goodness of fit. The premise behind this test that I'm sure that you guys all went out and did is the M&M company says that they have certain percentages of the different colors of M&Ms. And so you got your package of M&Ms, you opened it up, you counted the different colors of M&Ms, and then you tested to see, like, was what you got, did it match what the company said? And the answer to that is no, because they've changed their proportions since they did this, and actually since statistics classes across the nation started using this particular thing, they actually stopped even reporting what percentages they have. They used to they used to say what percentages of each color there were, but yeah, they don't do that anymore. But anyway, so what you did was you counted, you saw like, oh, hey, this doesn't match. Now, the reason why we have to use this kind of test and not what we did for like the T or the P, the T test or the Z test to get our P value, is because as one percentage goes up, say the number of blues, let's say your percentage of blues goes up, that's going to change the percentage or the proportion of the other colors, at least one other color, because they all have to add up to be 100%. They have to add up to 1. So as one of them goes up, something else is going to have to go down. And so they're not independent of each other, and so those other types of tests don't really work. This is a generalized version of what those other ones were, but it is a bit different. So anyway, the M&M experiment, what you did is a chi-squared test for goodness of fit. Again, one of the fun things about statistics is we get to use cool words like goodness and goodness of fit. What you did to find your chi-squared statistic, and this is how we always find a chi-squared statistic and throughout all the different types of tests that we're going to see today, the chi-squared statistic is always found this way. It's the sum of the observed minus expected squared divided by the expected. Or O is the observed, E is the expected number for each of the different categories. Notice we're using the numbers, not the proportions. So if you had proportions, like in the M&Ms, it tells you what proportion of each. You have to take that and multiply by the total number of M&Ms that you have to see what you would expect for each of those different categories. And as always with expected values, I'm using air quotes there, we might not actually expect to get that many M&Ms. Like it might turn out to be that we would have expected 8.72 M&Ms. Well, we're not going to get that. We could get 8, we could get 9, but we're not going to get those decimal numbers unless you're counting half M&Ms, which still you wouldn't get 0.72. You wouldn't be that exact. The larger the chi-squared, the more evidence against H naught, and we'll see what those hypotheses look like for the different tests and stuff in just a minute. But the larger the chi-squared means the smaller the p-value, so the more evidence against H naught. Same thing with the z and the t values. The larger the z or t, the smaller the p, and so the more evidence against that null hypothesis. The degree of freedom, it's the number of categories minus 1. Now this is something that's going to change when we get into different types of tests. But for our goodness of fit, it's the number of categories minus 1. So for the M&Ms, if I remember correctly, there were 5 different colors of M&Ms. Those are the 5 categories, so our degree of freedom there was 4. And then we find the p-value on the chi-squared distribution table. We're going to see that a couple times actually today. And now the p-value, it's going to be kind of like the t-table as opposed to the z-table, where we won't find the exact value. We're going to figure out what values it's in between, what critical values it's in between, and that'll tell us whether or not it is significant. Now, we will also see how to do this on a calculator, not actually in the lesson, but your assignment for this chapter has you using a calculator to find this stuff, and it'll walk you through that step by step. Properties of chi-squared distributions. And the opening page of this, the opening slide, actually had a chi-squared distribution, or a couple of them, and I'll bring that back so you can see it. But properties, it's only positive, which is different than the z and the t distributions, which were centered at 0, and they had both positive and negative values. These are only positive, which, when you look at the equation, this is going to be positive because we're squaring it. Divide by the expected number, we're going to expect a positive number of things. And so that's positive. You add a bunch of positive numbers together, you're going to get a positive value. In fact, it'll only be 0 if your observed and your expected were identical. It's going to be skewed to the right. So we're going to have a lot more close to 0, and the further away from 0 we get, the smaller that's going to be. And we'll see that in the graph. It's specified by one parameter, the degree of freedom. So it's not standard deviation, mean, nothing like that. It's only the degree of freedom. The area underneath the curve is 1 because this is a density curve still. All of them except for with a degree of freedom equaling 1 start at 0 and approach the axis asymptotically. And we'll see that in just a second when we see the graph too. And then it's more normal as the degree of freedom increases. So the more categories we get, the more normal it is. Now, we don't usually have that many categories, 5, 6, 10 maybe, but we don't usually go above that, even though the table goes well above that. And so what do these look like? So this is that graph that we saw on the first slide, the title slide. So the degree of freedom equaling 1 is this one here, which is actually asymptotic to both axes. Now, a degree of freedom equaling 1, in our case here, means that we'd have 2 categories. Now, with 2 categories, we probably wouldn't use a chi-squared test. We'd probably use the t-test, comparing the two things. Degree of freedom equals 4. We can see that it starts down here and goes up and then back down. And notice the degree of freedom equaling 8. It's closer to that normal distribution. It's still not normal. It's still skewed to the right, but it's less than, say, the degree of freedom equals 4. And the higher the degree of freedom, the more pulled over it'll be, and so the less or the more normal it will be. Again, notice it's all positive. We have the axis here as opposed to in the middle. And yeah, that's it about there. So our chi-squared table looks like this, where notice we have our probabilities here. We have the degree of freedom over here, and then the chi-squared values are all the values in the table itself. So what happens is we're going to find our chi-squared value using the formula. We added up the observed minus expected squared divided by the expecteds, and we get something like the chi-squared equals, I'm just going to say 17. Now, chances are it's not going to be an even number like that. It's going to be some sort of a decimal, but that's fine. And we have a degree of freedom equaling 5 because we had 6 different categories. So what we do is we go to our degree of freedom equals 5 line, and we go over till we get to where 17 would be, which would be right in between 16.75 and 8.39, which tells us that our p-value is in between 0.005 and 0.0025. So 0.0025 is less than p, which is less than 0.005, which is all less than 0.05 or less than 0.01. And so in this case, if we got these values, this would be strong evidence to reject the null hypothesis. It would be strong evidence. Well, we haven't gotten to the null hypothesis yet, but it is strong evidence to reject the null hypothesis because that p-value still means exactly the same thing as the p-values have always meant. That's the probability of getting the results that we got if the null hypothesis is true. So what is the null hypothesis for goodness of fit tests? The null hypothesis is the actual population proportions are equal to the hypothesized proportions. So, and then the alternative hypothesis is they're different than the hypothesized proportions. So if we were doing the M&M experiment, and this is the data that we got, or the results that we got, there's strong evidence to reject the null hypothesis that the M&Ms are distributed according to what the company had said at the time of the writing of the problem. It was actually old information even then because it has you go and look up the information. But it's not distributed according to that laid out percentages. It doesn't tell us what it is. It just says it's not what it says that it is. Our conditions for goodness of fit tests. We need an SRS. I didn't even put SRS there. I mean, we have to have an SRS. When we got the M&Ms, this always happens right after spring break. And so during the week of spring break, I go to a variety of stores and buy M&Ms. That way they're not all coming from the same box or the same batch or anything like that. And then each bag of M&Ms should be a general distribution from whatever was there. So it's an SRS. All individual counts are at least 1. So we have to have an observed thing. So we have to get at least 1 of every color in ours. And no more than 20% of the expected values are less than 5. So if we have 5 different colors, we can have 1 color that has fewer than 5 that we are expecting. Now, if we know what the hypothesized proportions are beforehand, we can get enough M&Ms, or we can have a sample size big enough to make sure that that works. Now, there can be a couple less than 5, depending on how many categories we have. And that generally happens when you have a fairly low percentage or low probability for that particular category. Ideally, you'd want them to all be more than 5, but it's a sample size thing. So that's how you know your sample is big enough. So those are the goodness of fit tests. And again, do the M&M experiment. It will walk you through a problem step by step. And it's wonderful. I generally don't get the tiny bag of M&Ms. I usually get the one that's a little bit bigger. It's like the 1.69 ounces or whatever, as opposed to the 0.7 ounces or 0.9, whatever it is. But I'd get that slightly bigger one. It's usually like $1.30 or $1.89 or something like that. And then when you're done, you get M&Ms. So it's kind of a win-win there. We're going to look at inference for two-way tables. So these are going to be another application of the chi-squared tests, allowing us to compare the proportions of success in more than 2 groups. And we'll also get into tests for independence and the homogeneity of a population as well. So when we are comparing these things, there's 2 big steps. The first is an overall test to see if there's any differences that we actually want to compare. That's what we're doing. That's the chi-squared test. The second is a detailed follow-up analysis to decide which parameters differ, which is something that you will get to in an advanced statistics class, but not something that we actually cover here. So, as I said, the overall test is a chi-squared test. We're going to find those values, the same that we did, and we'll see those again, take it to the same table, and get the same kind of p-value. So with a two-way table, we need to arrange the data in a table that shows both successes and failures, and we'll do a problem like this here in just a minute. And then our expected values, because this isn't going to be like the M&M population where we have expected proportions that they tell us. The expected values, because we have a variety of different things, we need to take the row total times the column total and then divide by the table total. And again, we'll do this. Conditions, again, SRS, all individual counts are at least 1, and no more than 20% of the expected are less than 5. So sometimes, I mean, it might be close, but ideally that's what you have. Sometimes though, the data you have to work with is low and you just have to kind of do what you have to do, but that's really where we want to be with that. So the chi-squared statistic, still the sum of the observed minus expected squared divided by expected. Larger chi-squared is still more evidence against the null hypothesis. The null hypothesis will change a little bit for these next kind of tests because we don't have, like, it doesn't, it doesn't fit in context what we had before. The degree of freedom here, this is different because we have more than just that one category, like of M&Ms. So the degree of freedom is going to be the number of rows minus 1 times the number of columns minus 1. Now, if we tried to do this with goodness of fit, our number of one of the two, depending on how you organize your data, it was 1 minus 1 would be 0, and the degree of freedom would be 0, and that would be problematic. And then we still find the p-value on the chi-squared distribution table the same as before. First one, chi-squared test for the homogeneity of a population. This is where we have the successes and failures. We set up a two-way table with successes and failures. It takes both. So our null hypothesis is going to be that all the probabilities of success are the same. Null hypothesis, they're not all the same, which doesn't mean that they all have to be different. It could be two of them are the same and one of them's different. And it doesn't have to be only 3 things. It could be as many things as you need. If you have 17 different things that you're testing, P1 through P17 would all be the same. So, a problem. So this is from the Iliad. If you haven't read it, I'd recommend it. It's a good book by Homer, not Homer Simpson, the other Homer. Anyway, what we have here is it gives an account of a lot of injuries. Some injuries to the body, the head or neck, and to limbs, and then some of them are going to be fatal, some of them are not going to be fatal. And so we have success and failure, which fatal is not usually a success, but I guess if you're on the other side, it would be. But again, remember, success and failure does not mean good and bad. It means, did we see what we were looking for, or did we not see what we were looking for? One of the other examples I was looking at was drugs to beat addictions. And you either relapse or you didn't relapse, and a relapse was considered success, even though that is definitely not a success. Even in the term of the experiment, it's not a success, but it just is. So remember, success, failure does not mean good and bad. So here we have our two-way table. The null hypothesis in our case would be the probability of dying with an injury to the body equals a probability of dying with an injury to the head, which equals a probability of dying with the injury to a limb. So if we wanted to write that, H naught, probability of body, is going to be the probability of head, the probability of limb. And then for the HA, I would actually write out pretty much that same sentence. Not all PB, PH, PL are equal. Like, it doesn't have to be just an equation. You don't want to put just a bunch of not equal signs, because that would imply that none of them are equal, when really, like, the probability of an injury to the body and the probability of injury to head could be the same or close enough to it statistically, whereas the probability of an injury to a limb is going to be different, which, thinking about it, that would not be it wouldn't be unlikely. Like, if you get hit in the head or the neck or the body, you probably have a higher chance of it being lethal than if you were hit in the limb. So now we need to make our expected table. So this is the observed. Now we need an expected table. So we'll have fatal, not fatal, and then we have body, head, neck, and limb. Now, so each of them, it's going to be the column total times the row total divided by the table total. Now, the table total is this 146. So now if we want to find this expected value, it's going to be 118 times 67, right? 118 times 67 divided by 146. which when we calculate it out, it comes out to be 54.15-ish. And then the one below it would be 118 times 45 divided by 146. So we get a 36.37. The one below it is 118 times 34 divided by 146, so 24.48. If you're wondering, of course I'm doing these all in my head right off the bat. I totally didn't set this up and have all the calculations already done beforehand. If we go over to non-fatal, the top one's going to be 28 times 67 divided by 146, which is 12.85-ish. The one below, 8.63. And the one below that is 6.52. So now each of these, we're going to take the observed minus expected, then divide by expected. So for that top left box, it would be 61 minus 54.15 squared divided by 54.15. And then plus the one below it would be 44 minus 36.37 squared divided by 36.37 plus ... We do that for the rest of them to get our chi-squared value is going to be 50.4. It's like 50.4063 or so, but 50.4 will be fine. Our degree of freedom, we have 3 rows, we have 2 columns. So the degree of freedom is going to be 3 minus 1 times 2 minus 1, which is 2. So with our chi-squared and our degree of freedom, we can look in our table. So we're looking at the 2 row. We get all the way out here, it's only 15.2, so our degree of freedom is way over there. That p-value is super small, which gives strong evidence against the null hypothesis. So our conclusion here would be that not all types of injuries are going to be equally likely to occur, or equally likely to be fatal. So not all injury locations are equally likely to be fatal. That'll be with a p-value of less than 0.0005, etc., etc. So that's the chi-squared test for the homogeneity of the population, and this right here was the same thing that you guys did, same thing that you guys did when you did the M&M experiment, as I strongly suggested that you did. So that's the chi-squared test for the homogeneity of a population, and that's, again, we have success, we have failure, but things aren't always success and failure. We have also independence, or association or independence. And so this is where you have multiple things. Like here we could have your grade level, like for the different classes, and the grade in the class, like A, B, C, D, F, and then 9th, 10th, 11th, 12th. And so does your grade level and your grade in the class, are those things independent, or is there some sort of association or relationship there? Same thing, one of the examples I was looking at as I was going through examples on what to do was plans after graduating college: grad school, job, other. And so and then they had different colleges. And so there were a bunch of different categories. It's testing to see, does it matter like what college you go to and where you go, like is those things related or not? So our our hypotheses for this, the null hypothesis is there's no relationship, which means that these variables are independent of each other. And that is always the null hypothesis here. It's like, oh, a chi-squared test for association. Null hypothesis, there's no relationship. What is this test about? What's the data about? I don't know. Doesn't matter. The null hypothesis, there's no relationship. And then the alternative hypothesis is there is a relationship between at least some of the variables. So here we're going to go back to the Iliad. And here, instead of fatality and stuff, it's the type of weapon used and then where the injury site was. So we have type of weapon, arrow, ground, or rock, and sword, injury site, body, head or neck, and limb. Notice we still have our totals here because we need the totals. If your data does not have totals in the table, you need to find the totals. You do that simply by adding. Now, what's important to note here is that this is one SRS that gets us this, and each thing falls into exactly one category. If you're hit with an arrow, you're hit either in the body, the head, or a limb. You're not hit in the body and a limb. It counts as one of them. Like, which one is it? Like, well, was the shoulder. You need to know if that's the body or a limb or the neck before you start. Like, it doesn't fall into more. Also, each injury is caused by exactly one thing. Maybe you're hit with an arrow and a sword. That would be two different injuries. So it would count as two different places. Maybe you're hit with an arrow and you fall off a ledge and you land on the ground or a rock. That again would be two injuries. You're not hit with an arrow that's strapped to a sword. That doesn't count. So each individual falls into exactly one box on this. And notice, like, not every individual that was there necessarily falls in one box because not everyone was injured. I mean, if you read it, pretty much the entirety of the Troy and the Greeks were injured, but not everybody that was at the Battle of Troy was injured, so you wouldn't necessarily fall here. This was just looking at, of the injuries, what happened. So we have these guys, our null hypothesis, alternative hypothesis. We need to find the expected values. So expected values again. We'll have arrow, ground, sword, body, head, limb. And notice once again, just like with the M&Ms, that we use the count, not the proportions. I mean, proportions can help us to find, like, to kind of look at the data, but we actually use the counts. So if you have proportions, you have to change them into counts. To find the expected value, it's the same as it was before. To find this one, it's the column total times the row total divided by the table total. So it's 67 times 12 divided by 145, and we come up with 5.54. And then we go 67 times 11 divided by 145 to get that one, which is 5.08. Now, so of your chi-squared values, the 5.54 will give you a smaller chi-squared, like that'll impact the chi-squared less than the 5.08 because we're looking at the differences between those guys. And then we can continue doing these. The 67 times 122 divided by 145 is going to be 56.37. And you might think, oh, wow, that one's like 5 away. That one's even bigger. But remember, we divide by that same number. So it'll be like 5 squared, then divide by 56.37. When you actually do the calculations, you can see what the numbers give you. Like this top, this This guy adds like 0.052 to our chi-squared. The second one adds 3.277 to the chi-squared, and this bottom one will only add 0.38 to the chi-squared. So by actually doing it by hand, use a calculator, but actually like going through the steps, you can see which pieces cause what, which is kind of nice sometimes, especially when you get into more of the follow-up. Anyway, when we continue doing this will be 45 times the 12, 11, 122 divided by 145. And so we get our expected values of 3.72, 3.41, and 37.86. And then we'll have 33 times 12, 11, or 122 divided by 145 to get 2.73, 2.50, 0, and 27.77. So now we can find our chi-squared value. Remember the chi-squared value, we're going to take the sum. So chi-squared will be the sum. We're going to have the observed minus expected, so 5 minus 5.54 squared divided by the expected, 5.54, plus, and then we do this for each of them, 5.08 minus 1 squared. I switched the order on those two. It does not make a difference because the only difference is whether it's positive or negative. I'm squaring it, so it will end up being positive. Divide by 5.08. What is important, though, is that the denominator is still the expected value. You don't want to switch that to be a 1. And then plus ... You add them all up, and we get the chi-squared here equals 10.4525. The degree of freedom, we have 3 types of weapon. We have 3 injury sites, so it's 3 minus 1 times 3 minus 1, so that's 2 times 2, which is 4. So we have our chi-squared, we have our degree of freedom. We can pull up our table. So here we're looking in the 4 column, and that 10.45 happens in between 9 point something and 11 point something. So this means that our p-value is in between 0.05 and 0.025. So 0.025 is less than p, which is less than 0.05. So here we have some evidence to suggest that we reject the null hypothesis, that there's no relationship. Not strong evidence necessarily, and depending on what our alpha level was before we started, maybe we needed an alpha level of 0.01, in which case we would not reject the null hypothesis. So in this case, the no relationship would be it doesn't matter what you get hit with, the injury site is just kind of random. So it's like equally as likely to get hit in the head with an arrow and a sword. It's kind of the same thing, or is what that's saying, that no relationship. Here, with a p-value of less than 0.05, there is some evidence to reject the null hypothesis, saying that there is a relationship between the type of weapon used and your injury site. So that would be the chi-squared test for association and independence. So that is chapter 13. That's all about chi-squared testing. You have an assignment where you're going to be doing this using the graphing calculator. The instructions are for the TIs. Apologies to those couple of you that don't have a TI. You can find one. I would recommend just like looking up, find an emulator for it if you don't have a calculator with you. Make sure you get that turned in. And other than that, we'll have a test coming up on this, or probably a quiz. This one's not, like, I've never actually given a test for this chapter. It's always been just a smaller quiz. But work problems. Do some problems in the book. Try these. Practice these. But until next time, keep working problems, keep asking questions, and as always, happy mathing.